We had seen previously that alkyl halides can be prepared by addition of HCl, HBr, and HI across the double bond, resulting in less or more highly substituted alkyl halides depending on the reaction conditions. We had looked at two modes of addition involving electrophilic addition under polar reaction conditions and also non-Markovnikov addition involving free radicals. One other way to prepare an alkyl halide is to use allylic bromination or chlorination reaction at the allylic position. The reagent that allows for allylic bromination is N-bromosuccinimide. We had seen this reagent used previously in halohydration reactions of alkenes. Under free radical reaction conditions, using light as an initiator in carbon tetrachloride solvent, we see that allylic hydrogen can be replaced with a bromine atom, and N-bromosuccinimide under free radical conditions serves as in situ source of bromine atoms, bromine radicals. Reaction is selective when N-bromosuccinimide as opposed to N-chlorosuccinimide is involved. Reaction is more selective for the replacement of the more highly substituted hydrogen. In this case, cyclohexene has 4 equivalent secondary allylic hydrogen atoms, and under allylic bromination reaction conditions, one of these allylic hydrogens is replaced with the bromine atom. This reaction is useful because allylic bromide can be successfully converted to conjugated dienes, and then conjugated dienes can be used in cycloaddition reactions. Base deprotonates an alpha hydrogen, alpha relative to the alkyl halide, and elimination of HBr gives us conjugated diene. The mechanism involves deprotonation by the base, expulsion of the leaving group, and formation of the pi bond. In the case of cyclohexene, as I had said previously, we have 4 equivalent secondary hydrogen atoms, and one of them is replaced with the bromine. In the case of an alkene, where we have different types of allylic hydrogen atoms, for example, here we have 2 secondary hydrogens, and here we have 1 tertiary hydrogen atom owing to the presence of the metal group on a tertiary carbon. Under the same reaction conditions, using N-bromosuccinimide with UV light as an activator, carbon tetrachloride solvent, and heat, when NBS is used, the more highly substituted hydrogen atom will be replaced with the bromine atom. And again, under these conditions, reaction is fairly selective. However, if N-chlorosuccinimide is used, NCS, the selectivity is much less. Here is another example of allylic bromination. Using N-bromosuccinimide, we look at the allylic hydrogen atoms. There are 4 of them, one at the tertiary allylic position, and we also have 3 primary allylic hydrogen atoms. Owing to the selectivity of NBS, we see that the tertiary allylic hydrogen is replaced and not the primary hydrogen atom. Addition of base KOH or NaOH and aqueous THF allows for elimination of the HBr hydrogen from the alpha carbon relative to the alkyl halide, giving us conjugated diene. Under the same reaction conditions, benzylic position, benzylic, next to the benzene ring, can also be brominated. Let's take a look at the chemical reaction here. And again, we'll use NBS, light, carbon tet, and heat. And we'll see that the major product will be secondary benzylic bromide, whereas the primary position remains unsubstituted. This reaction, as we'll see in a subsequent chapter, will be useful in preparation of styrene derivative. So again, NBS is selective for the more highly substituted benzylic and allylic position.